Hey, AP Calculus students, Mr. Meunier back again. Today I want to talk about topic 5.6 and 5.7. These topics deal with the second derivative of a function and concavity initially with that. Now, concavity is kind of the shape of a curve. It's kind of like a bowl shape to a curve. So for instance, this piece in the bottom left of our function 1 over x minus 1, this would be a concave down shape. While the upper right side of this function is a concave up shape. Concave down and then a concave up. I think of these as being like a bowl of cereal and milk, maybe. Concave up, that cereal and milk will stay in the bowl. You're kind of holding that material inside of it. While concave down, everything's going to fall out. It's like it's tipped upside down. And there's 4 real shapes to concavity, I would say. I'm going to sketch these out, but you have this. That would be an increasing function with a concave up shape. Increasing and concave up. While if I have something like this from left to right, that is decreasing while it's still concave up. Increasing concave up, and this would be a decreasing concave up. And then you also have something like this could be a shape where this would be decreasing and concave down. And finally, we can have decreasing and concave up. And that's what this last piece I did is. So those are kind of the 4 shapes to a curve. And if you really break them down and piece them together, they're one of these 4 things. Why that's important now for us, we discussed last couple classes, if a function is increasing, that means its derivative is positive. Oops. Guys, I messed up this last one. I didn't want this part here. Let's erase that. I want an increasing concave down look, an increasing concave down look. So if we are increasing and concave down, it's going to look like that. That's the 4th piece I wanted. I'm sorry, I repeated one from before. Went brain dead there. So yeah, sorry about that. So if I have an increasing problem, that means it's a positive derivative. So again, this one on the far right, from left to right, that is increasing. That means the derivative is positive. While if a problem is falling from left to right, decreasing, that means the derivative is negative. Concavity now, this new piece relates to the second derivative. Concave up means the second derivative is positive. Concave up means the second derivative is positive, while concave down means the second derivative is negative. So those are the 4 possibilities. If you compare the first and second derivatives, you can get these different shapes. And that's what this piece is discussing. If the second derivative is a positive number, a curve is concave up. If the second derivative is a negative number, the curve is concave down. If you change concavity, that is called a point of inflection. Point of inflection. And that would just be that the second derivative changes signs. It doesn't necessarily have to be positive to negative or negative to positive, but either of those. If the second derivative changes signs, you will change concavity, and that is called a point of inflection. It's not a max or a min. It's a point of inflection. Okay. Now, the first derivative, point of inflection, is going to occur where the second derivative equals 0 or the second derivative does not work, not differentiable. This second derivative equal to 0, I don't want to call it a critical number. Critical number is first derivative specific. So I will just sometimes call this an important number. That's not an official term. That's not going to be in a textbook, but to differentiate that from the first derivative. First derivative 0 is a critical number. Second derivative 0, I call an important number. Critical number is specifically relating to the first derivative. So again, a point of inflection will occur when the second derivative equals 0 and your second derivative changes signs. All right, so we're not going to do all of these, but I want to do one to kind of get the idea of this. Determine the open intervals on which each, so again, this is an open problem. Whenever I see open problems, I kind of have to do a number line and test values. Determine the open interval on which each graph is concave up or down and state any points of inflection. So again, whenever I see concave up or concave down or points of inflection, that tells me second derivative, second derivative, second derivative. Max, min, increase, decrease. Those words mean first derivative. Max, min, increase, decrease are first derivative. Concave up, concave down, point of inflection is a second derivative. So I have a function. I need to get the derivative of it. So that's 4x cubed minus 12x squared. Then I'm going to need the second derivative, which is 12x squared minus 24x. I want to find the important numbers for this. So that just means second derivative equal to 0. 12x squared minus 24x equal to 0. We want to solve this. We can factor a 12x out. That's going to give us an x minus 2. When we solve this now, 12x is going to give me an x equal to 0. X minus 2 is an x equal to 2. Those are the important numbers. You would also have important numbers if the derivative does not work, if it's undefined. But if you look, this second derivative, it's not a fraction. There's no unusual pieces. It's not going to have any of those spots. So once we get that done, we want to build a number line, put 0 and 2 on that number line. Those are important spots, and test around that. And I'm going to test it in the second derivative. So if I test -1 for this first region on the left, inside the second derivative. And I like to plug this when I do a test into the factored pieces. 12 and a -1 is a negative number. -1 minus 2 is a negative number. Those two negatives give me a positive. If I test out f double prime of 1, 12 and 1 is a positive number. 1 minus 2 is a negative. That gives us a negative. If I test out f double prime of 3, we're going to get 12 and 3 is a positive. 3 minus 2 is a positive. That makes a positive number. So because of that, we know f of x is concave up from -infinity to 0. This first section, positive is concave up. Also concave up from 2 to infinity. It is concave down from 0 to 2. So we will say f of x is concave up from -infinity to 0 and 2 to infinity because f double prime is greater than 0. And we can also say f of x is concave down from 0 to 2 because f double prime is less than 0. So those are your intervals of concave up and concave down. Points of inflection. Point of inflection. That occurs when your second derivative equals 0, when you have an important number, which is 0 and 2, and you have to change signs. And notice at 0, we go from a positive to a negative. So that's going to be a point of inflection. And at 2, we go from a negative to positive. Now, point of inflection, point means x and y. So x equals 0, x equals 2. Will have POI. What's the y value with those? Well, if I want a y value, plug back in the original problem. So f of 0 equals 0 to the 4th minus 4 times 0 cubed, which is 0. And f of 2 is 2 to the 4th minus 4 times 2 cubed, which is negative 16. So we have POI at 0, 0 and 2, negative 16 because f double prime equals 0 and f double prime changes signs. Okay. And the curve for that looks like this. Again, we had concave up from negative infinity to 0. If you notice this curve right here, from negative infinity to 0, it's an upward bowl. It was concave down from 0 to 2, right? And this where my hand is there. That's a concave down section from 0 to there, kind of an upside down bowl. And then from 2 to infinity, it turns back to a concave up right side bowl. POI at 2, negative 16, that's where the change is, and at 0, 0. All righty. So that's the process, and that's how example B and C would be. I'm not going to work through those, the keys and the notes for those, but it's the same idea. Do the second derivative, put it equal to 0 to find important numbers. If it's as a fraction, find out where that denominator equals 0 for more important numbers, plot them on a number line, test values. There's the curve. It's also. Now 5.7 is something called the second derivative test. This test lets us use the second derivative to find maxes and mins. Max and min is typically a first derivative idea, but this can work because if you have derivative equal to 0, first derivative equal to 0 is a critical number. Critical number tends to be a max or min. So if I have a critical number and the second derivative is a positive, so second derivative positive means concave up. If you think about that, point critical number, the curve around it is concave up. This point is going to be a minimum. Whereas if I have a critical number and the curve around it is concave down, second derivative is a negative number, it would look kind of like this. You have a point, critical number makes a point, around it is an upside down bowl. That's going to be a max. So if our critical number is a positive second derivative, that makes a minimum. If our critical number is a negative second derivative, that makes a maximum. And this is called the second derivative test. Okay. It's used to find max and min. So it combines your two derivatives. So find the relative extrema. Again, extrema means max and min using the second derivative test. So to make this happen, I need critical numbers. Maxes and mins happen at critical numbers. That's going to be derivative is negative 15x to the fourth plus 15x squared. Put this equal to 0. Find the critical numbers. I can factor a negative 15x squared out of this and get x squared minus 1. From here, we can see that we have x equals 0 is going to be a critical number. X squared minus 1 is going to give me x equals 1 and x equals negative 1. So these three spots are potential maxes and mins because they're critical numbers. It's where the derivative equals 0. Then I want to find the second derivative. So f double prime is going to be negative 60 x to the third plus 30x. That can factor a little bit. If I take negative 30x out, you're going to get, what is that, 2x squared minus 1. Yeah. So we don't have to factor, but I think it helps to check things out. Now, plug our critical numbers into this second derivative. I only care if it's positive or negative. So if I plug 0, and since I factored, I want to plug it in here. I'm going to get 0, 0 times anything. 0 times anything equals 0. Now, 0 is not a positive or a negative, unfortunately. So that's inconclusive. It doesn't tell us max or min. It doesn't quite work. But if I plug in a 1, negative 30 times a 1 is a negative number. 2 times 1 squared minus 1 is a positive. That makes a negative, which again means I have a critical number in a concave down situation. Concave down in a critical number means we have a max at that location. If I plug in negative 1, well, negative 30 and negative 1 is a positive. That's going to be another positive. 2 times negative 1 squared minus 1, that's a positive. That means second derivative positive is concave up. That means we have a minimum. A minimum. Okay. If I want the y values that go with these locations, I got to plug it back in the original. So we have relative min at x equals negative 1 because f prime of negative 1 equals 0 and f double prime negative 1 is a positive number. We have a relative max at x equals positive 1 because f prime of 1 equals 0. The first derivative is 0. And f double prime of 1 is a negative number, less than 0. And again, if I want the y values with these, I plug it back in the original. Back in the original. All right. And then last, table problems. So given the values below for x, f of x, x prime, along with the fact that f prime has only 2 zeros on the intervals negative 3, 10, and f double prime has 2 zeros on the interval negative 3, 10, answer each of the following. This is just telling us this stuff that there's not more going on. There's not hidden stuff, not in the table. The table is kind of giving you all the key pieces. Identify all x values where f has a relative minimum. Justify using the first derivative test. So again, mins and maxes tend to happen when your derivative equals 0. So there's 2 locations where the derivative is 0. First derivative test, minimum. That means, again, if I have a minimum value, down below, we go from decrease to increase. We have to change from f prime negative to f prime positive. That's the first derivative test with f prime 0 in the middle. If I look at my table, critical number of 0, well, -1 is a critical number, but it goes from a positive to a negative. That is not a minimum. 0 goes from a negative to a positive. That is a minimum. Critical numbers also happen when the derivative is undefined. So I shouldn't neglect this at x equals 7. Notice the derivative goes from a +2 to a +3. Stayed positive, that's not a min or a max. So we're going to say x equals 3 is a max because f prime of 3 equals 0 and f prime changes from negative to positive. And this is not a max, obviously, this is a min. X equals 3 is a minimum because f prime of 3 equals 0 and f prime change from a negative number to a positive number. Part B here, I'm not going to try to lose this, I'm going to kind of do it above. Identify all x values where you have a relative max, use the second derivative test. So maxes and mins, again, happen at a critical number when derivative is 0 or undefined. Second derivative test means if I have a max, it's going to look kind of like this picture. That's going to be a concave down. So a negative second derivative, f double prime negative. So if I look at x equals -1, I have a critical number of 0. Notice the second derivative is a negative. That's going to be a maximum. 0 here, or 3 we already did. It's a critical number with a positive second derivative. And then here at 7, undefined is a critical number. 0 is inconclusive. It doesn't tell us anything. So I'm going to say x equals -1 is a min because f prime -1 equals 0 and f double prime of -1 is less than 0. That's your justification. All right. Then identify all values where f has a point of inflection. Point of inflection occurs when you have an important number, when the second derivative is 0 or undefined. So if I look at this, second derivative is 0 at +1 and at 7, and you have to change signs around it. So important number, before that is a -1, after that important number is a +2. It changed from a negative to a positive. At 7, we have an important number, +3 before it, +5 after it. It did not change. So x equals 1 is a point of inflection because point of inflection occurs at x equals 1. Because f double prime of 1 equals 0 and f double prime changes signs at x equals 1. All right, then last, write the equation of the tangent line. We always need the x value, the y value, and the slope value. We know x is 5. X is 5. The original problem will give us the y value. So if x equals 5, f of x is the y, and then the derivative leads you to the slope. So x is 5, y is 3, slope is 2. X is 5, y is 3, slope is 2. So x is 5, y equals 3, slope is 2. Y minus 3 equals 2 times x minus 5. That's the equation of a tangent line. And you don't have to simplify that ever typically. If you wanted to, we could distribute, move the numbers over, but I would stop right there. All right, y'all. Hope you're all doing okay. Hope to see you soon. Bye.